Good afternoon, guys. I'm just going to create a quick video here. I know a little different than what you've seen before. Gonna try and work this out. I don't have a stylus, but I think we can make it work. I am going to be doing one or two full circuits with 3 loads. So we're going to be looking at a RLC 3-phase circuit. The one difference is I'm not going to draw all the lines between all of the loads just for space on the screen. But hopefully everything ends up going well. Okay, so first off, let's do a we're going to do a Y connected alternator. We're going to do a delta capacitive load, let's do a delta inductive load, and a resistive Y load. All right. Let's do 600 volts as our E line. So that'll be there. So E line is equal to 600 volts. We're going to do, for the capacitive load, 5 ohms per phase. The inductive load is going to be 8 ohms per phase. And the resistive load, so that's capacitive, inductive, and resistive. Let me just get rid of that quick. So we said 8 ohms per phase, and the resistive is going to be 10 ohms per phase. All right. If we have 600 volts per phase, we are going to be looking at a capacitor in this circuit, or 5 ohms per phase. So we've got 5 ohms per phase, and if we end up coming over to the capacitor, let's break down the voltages first, what we're going to have per phase. So E phases all the way across, E phase. If we have 600 volts in the line and we come to delta, when we go to drop into the delta, we know that voltage in the line and the phase is the same, so we're going to end up getting 600 volts for a phase voltage. When we get to our delta inductive load, it's also in delta, so we're going to end up having 600 volts per phase again. And when we get to the resistive load, as well as with the alternator, we are actually splitting the voltage between the two loads. So if we look at the alternator on the far left, this load here, or this coil and this coil, are both producing a voltage that produces 600 volts, so it's going to be root 3 smaller than 600. So 600 divided by root 3. And just for ease, on here, we will keep it, it's whatever, 346.4. We'll just have it at 347 volts at my alternator, and then we would also have the 347 over at our resistive load, and those are in volts, obviously. Let's get rid of that now. All right, so 347 on the resistive load divided by 10 ohms So let's move this back. 347 volts divided by 10 ohms is obviously 34.7 amps. So our I phase is going to equal 340 or 34.7 amps. And I'm doing this with my fingernail because I noticed that my stylus sucks. So bear with it looking like a 5-year-old doing it all. All right. And now we're looking at our power, our three-phase power. And for three-phase power, as you know, we get 347 times 34.7 times 3. That's using our phase values. And that would be our E phase times I phase times 3 formula in order to calculate that out. Okay? So we end up getting from that 347 times 34.7 times 3 is 36.123 kilowatts. All right, so that's that one done. Now let's look at our inductive load. And with the inductive load, we want to find current. I phase is equal to 600 volts divided by 8 ohms. So 600 divided by 8 is 75 amps. So I phase is equal to 75 amps. And if we use the same formula we used before, the E phase times I phase times 3, we end up getting 600 times 75 times 3. And I'm erasing things as we go, obviously, because I don't have a lot of room here. So 600 times 75 times 3, 135 kVARs. $135 kVARs. And that's inductive. Oh. Excuse me. Okay, so that is that one. Now let's do our capacitive value. And we want to find current first. So our I phase is equal to 600 volts divided by 5 ohms. 600 divided by 5 should be 120. So that's 120 amps. Excellent. And then now we are going to be looking at our total power. And our power is going to be 600 times 120 times 3. So we get 600 times 120 times 3. And we get 216 kVARs capacitive. Yeah, 216 kVAR. is capacitive. So 216 kVAR, 135 kVAR, and 36.123 kilowatts. All right. So that is good. We are now going to get rid of these up here to make a little more room. When we end up coming into our line values for the resistive load, if we had an amp clamp around that phase and then came up into the line, we're not adding another phase to that. So our I phase and IL will be the same. So up here we know IL is equal to 34.7 amps. And remember, when we're doing vectors, the line current is what's being used when we go to plot it to use Pythagorean theorem. Now we do IL of the inductive load. We have 75 amps per phase that are being drawn by that coil and then also that coil. Obviously, it won't be twice the size when we come up into our line value. It'll be root 3 larger. So 75 times 1.732 or root 3 is 129.9. 129.9 amps. And that's our line current of the inductor. Now the line current of the capacitor. And we're going to be doing the same thing. So 120 times 1.732. We get 207. 207.84 amps. And we had just taken that 120 and multiplied by 1.732. This one was, the inductor was 75 times 1.732 or root 3. And then obviously the Y-connected resistive load, the current would be the same. All right, so let's now erase everything in the center. Hopefully I don't erase something that I need. Okay. So now we want to do Pythagorean theorem, and we need to take our, let's look at our net current. Our net current is going to be our capacitive current, 207.84, and because capacitive more, it's obviously going to be capacitive, more capacitive than it is inductive. Take away 129.9, and our net current is going to be net is 77.94 amps. So let's write that up here now. 77.9. I am brutal with this. 77.94 amps. I think I've gotten worse as this videos went on. So let's plot that. So it's more capacitive, so it's going to be up. So our triangle is going to be like this. 77.94 up and 34.7 amps. Here is our resistive, so we want to look at what the hypotenuse is. So 77.94 times 77.94. And obviously we're doing a squared plus b squared is equal to c squared. And then that was bad. And we get 85. I accidentally had erased the whole thing there. We get a hypotenuse of 85.32 amps. Once we do that, so it ended up being the square root of a squared plus b squared would give us the answer. Let's get rid of all that. So we now know that our line current up, oh crap, erase that. Good thing there's backspace. So our line current over here is 85.37 amps. That's our I line. And because it's in Y, when we come down, our current per phase is going to be the same per line. So our I phase and our I line are both going to be 85.37 amps. I'm now going to just erase all that. And now we'll do our last vector. Make this a little bigger. And now we're going to do our power triangle. So we know that our true power, 36.123 kilowatts, is going to be on the bottom. And then our net VARs, our net value is going to be over here, which is going to be 216 kVARs. Subtract 135 kVAR. So 216 subtract 135, so we have 81 kVARs. That is our net value. So then now we're going to do Pythagorean theorem again. Here. So we do 81 squared plus 36.123 squared. And we get 88.69. And that would be kVA. So that would be your total power consumed, 88.69 kVA. And then the other thing you can do is, so that we got all those values. I'm just going to erase this. If we look at our total power or total apparent power, we can do 347. This is just a double check, times 85.37 amps times 3. So 347 times 85.37 times 3, and we get 88.87. 88.87 kbars. So that, or kVA, sorry. So that'll be just a little bit of a rounding issue throughout, rounding up or down in different cases, but these two values are very close to the same. So using Pythagorean theorem or just calculating out with the values that we found, they are very much close. So obviously we did that right, and now we are just going to calculate what our power factor is. So I'll use the Pythagorean theorem one as a value, and as you know, with power factor, we are true power over apparent power, and so we have 36.123 kilowatts divided by 88.69 kVA. I'm going to go and buy a stylus later today, a better one. And so 36.123 kilowatts divided by 88.69 gives us a true power of 0.41. Or apparent power, of 0.41 or 0.407 or 41%. And this would be capacitive, so it would be leading, so 41% capacitive. That's everything with that. The next video, I'm going to start going into word problems. And I'm going to be handing out on Friday, or your next class, the questions for you to work on. Okay, hopefully that's good. I'm not going to go over anything more in this video. I think we've got enough there, so I'm going to